So in mathematics, you've probably seen the cross product and the dot product before. We've already discussed what the dot product is, so now we want to move on to the cross product. And I want to first mention that the cross product is extremely crucial for the mathematical study of magnetic fields. So if you have two vectors, let's just say A and B, at an angle of theta to each other, then we define the cross product as follows. So keep in mind, in mathematics, the cross product or the vector product is what's called a binary operation. So what this means is you have this binary operation on two vectors, and it's going to be in three-dimensional space. That if you have two independent vectors like A and B, then your cross product is going to be a vector that's perpendicular to both of those original vectors that you started out with. So if we have vectors A and B, then A crossed with B is equal to the magnitudes of A times B sine theta. And we want to first mention that the direction of the vector A crossed with B is perpendicular to the two vectors, or normal to the plane that contains them. So this over here is the magnitude of the cross product, and this over here basically tells us that the direction can be determined very easily if we stick to certain rules. And those rules are called Fleming's right-hand and left-hand rules. So I want to say direction can be determined easily using Fleming's right or left-hand rules. So naturally, our discussion is going to lead us to those two rules. Pick the one that you're most comfortable with and stick with that one because both of them work. So number one, I want to talk about Fleming's left-hand rule. And then I'll talk about Fleming's right-hand rule. So let's just scroll down. And now, just to test my drawing skills, that's supposed to be a thumb on some sort of palm, index finger, middle finger. So there's my left hand, and essentially if I want to use Fleming's left hand rule with my thumb pointing up, my index finger pointing this way, and my middle finger pointing slightly out of the page, I can label this as A, B, and C. So essentially what I'm looking at here is some sort of origin, A, B, and they're at right angles to each other, and C over here is going to be at right angles to each. So now we look at the right hand rule. Let's kind of draw the opposite of this. So there's my thumb, and I have my index finger. My middle finger, my fingers are getting worse and worse. Oh, that was even worse. Okay, well, I've given up on the pinky finger. So I have my right hand. It's a pretty mangled right hand. So I want up to be C, I want this to be A, and I want this to be B. And so what I'm looking at here is some sort of origin point. I have A with B, supposedly at right angles, and then I have a C pointing upwards, also at right angles to each of these vectors. So the key thing between the two of these is that C is the direction of the cross product of A and B. So just a quick recap, just remember to pick either Fleming's left hand or right hand rule when you're doing the cross product so that you can keep to a consistent convention. The next question I want to ask then is, if I know that C is going to be normal to the plane that A and B are on, how do I know if it's pointing up or down? Because technically, if I want something perpendicular, it can go one of two ways. So how do we know if the direction of A times B equals C, where A crossed with B equals C, is positive or negative? And we want to follow a convention, so let's follow this convention. For each coordinate system. Remember, we have the Cartesian coordinate system, we have the cylindrical coordinate system, and we have the spherical coordinate system. And we're looking specifically for 3D coordinate systems because if you have a cross product, it has to exist in 3 dimensions. So with the Cartesian coordinate system, we had x, y, and z. The cylindrical coordinate system had r, phi, and z. And the spherical coordinate system had r, theta, phi. So what is our convention? It's essentially this. We want to move forward in a specific order. We're going from x to y to z, and then repeat. R goes to phi, which goes to z, and then it comes full circle. For spherical, R goes to theta, which goes to phi, and then we repeat. So the convention is if we are doing a cross product in the order of these arrows, then it's in the positive direction, and our final cross product is going to be positive. And if we're going backwards, then our final cross product will be negative. So let's go through a few examples. When we go with the arrows, the cross product is in the positive direction. So if I do, let's just do examples. If I do x crossed with y, x going to y is in the order of which these arrows indicate, so therefore it must be positive z. That is my answer. If I look at the cylindrical coordinate system, maybe I want to do phi crossed with z. Phi going to z is in the direction of the red arrows, and therefore the remaining vector or unit vector is r, and it's in the positive direction. Looking at spherical coordinates, what happens if I go from phi to r? So now I have phi crossed with r, it's going to give me positive theta. So then we have to do the opposite. When we go against the arrows, the cross product is in the negative direction. So let's work through a few examples ourselves. Let's now go and do a cross product between x, or y and x in that order. So y going to x is the reverse order of this arrow. It's going against that red arrow, so therefore I have negative z as my answer. What happens if I go from z in cylindrical coordinates to phi? That means I'll have negative r. And if I look at spherical, what if I go from r crossed with phi? That's going this way, which is against the red arrow, and that means I end up with a negative theta as my solution. So hopefully that gives you a good overview of just the sign convention that we use for cross products. It will become very important in later chapters and examples for you to quickly be able to determine the direction of these cross products.